Hello everyone, so let's start our lecture for today. We just finished the discussion on the design of horn antenna. So I'm gonna now move on to a different type of antenna, which is reflector antenna. But before doing that, maybe in this lecture we can start by discussing why we need to go to an antenna such as reflector antenna. So maybe start our discussion with revisiting some of the directivity values that we have for antenna. So for lambda by 10 dipole antenna, we saw 1.5 dimensionless directivity or 1.76 dB. We saw that we increased the length of the dipole and therefore we increased the directivity from 1.5 to 1.64, and this is the dB value. We also studied monopole antennas based on the way that directivity is defined. Monopole has twice directivity of dipole of the same lengths, the same corresponding lengths. For example, lambda by 10 dipole correspond to lambda by 20 monopole. And as you see, if this is 1.5, this is times 2, which is 3, or in dB scale would be 3 dB more, which is 4.76. And we had the same thing, lambda by 4, which correspond to half a wavelength dipole. If this is 1.64, this is 3.28 or 3 dB more. We also looked at a small loop and also a loop of circumference lambda. For the loop of circumference lambda, we saw it in the lab and also in the lecture, mainly in the lab. And if we had the loop of circumference lambda, the main beam was along the axis of the loop as opposed to a small loop antenna. And this is the directivity. We also discussed half a wavelength slot antenna, and this was the directivity. As you see, this is essentially similar to half a wavelength dipole antenna. Then we also talked about open-ended waveguide antenna. You remember that A and B in open-ended waveguide antenna needed to follow certain sizes based on the type of waveguide. This is, for example, WR9T, which is for X-band. The directivity is mentioned here. Microstrip antenna or patch antenna, typical directivity is from 3.5 to 6.5 or 5.4 to 8.1 dB, just typical values. And for pyramidal horn antenna, typical directivity that you may use 10 to 110 dB to 20 dB. So these are some directivity that we have. Now the question is, if you want more directivity, for example, if you want directivity of 1000, which is 30 dB, or 10,000, which is 40 dB. So what would you do? That's essentially the question that we have. One way to answer this would be to say, okay, you can use some of these antennas. For example, you can use several horn antennas, make an antenna arrays, and then increase the directivity. That's one way. Of course, that then requires feeding network and everything. So this discussion, when I'm saying I want to increase the directivity, let's say to 10,000, I mean using a single antenna element, not multiple antennas, because that also has complication if you want to use multiple antenna system. So that would be the discussion here. For example, if you are to use multiple horn antenna, you remember we had an approximate formula to estimate the directivity of the antenna array, and that's just completely approximation to start with under certain assumption. But the basic approximation was that if you want to go from 100 to 10,000, then perhaps you're looking around 100 antenna to take it to this level. So that's so you see you end up having lots of antennas, which might complicate things. Now, so here we're looking for single antenna element. Then you might say at that point, why not just use the horn antenna and design a horn antenna such that we get to 10,000 directivity, for example, or 1,000. I'm focusing on 10,000 for this discussion. So this is my question now. Why not just use a pyramidal horn antenna, but design it in a way that we get to 40 dB or 10,000 directivity value. So let's answer this question. So let me remove these things. And I'm just going to keep horn antenna. That's the typical directivity. But imagine we wanted to get to 10,000, for example. So that's my purpose. So I'm going to say D naught is 4 pi lambda squared. I have my aperture efficiency. I have my physical area. So this is what I have here. And aperture efficiency of horn, we said let's have it as 51%. But here, for the sake of simplicity of calculation, I don't want to go to the detailed calculation. I'm just assuming the best case scenario, which is not going to happen. So I'm just going to assume aperture efficiency is 100%. Again, that's not going to happen because, as you know, when you get to the aperture of the horn, you have two issues. First of all, you don't have uniform field, so therefore you cannot be at 1. And also the fields are not in phase, so you're going to be somewhere around 51%. But for the sake of discussion, let's assume that directivity is 10,000. This is 4 pi lambda squared. And aperture efficiency, for the sake of discussion, let's assume is 1, and then you get to your physical area. So based on this, we end up with the physical area of lambda divided by 2, 4 pi, and 10,000. So this is the physical area that I need to have. Now, what is my dimension? What is my physical area? So the physical area of a horn antenna, as you remember, we had two cross sections for horn. So one of them was A, the other one was B. So this one was of course B, this one was my A. So that was the aperture of the horn, and if you look at the aperture of the horn, you essentially see a rectangle, A and B. So this physical area is essentially A times B, which needs to be lambda by 2, 4 pi, 10,000. So this is what we have under this simplified assumption. Now, I need to, of course, know my A and B. Again, I'm going to do some approximation here because this is just a very, discussing this in a crude way. So instead of finding A and B for my design and so on as we did, we just say, let's assume that they're pretty much the same. That's not the right assumption here, but let's, for the simplicity, let's do that because then I can find my A and B without going to further equation. So if I assume A is equal to B, then what's going to happen is that I'm going to have A squared equal lambda 2, 4 pi, 10,000. So this is what I have. And just to be clear, in the exam, if I happen to ask you to design horn antennas, don't use this type of approximation that I'm doing here unless I tell you that you can use this type of approximation. The only reason I'm doing it here to simplify so you can see immediately without going to too much math. So I'm assuming A is equal to B here for simplicity. So your A squared is going to be equal to that. Therefore, your A becomes lambda. So I'm taking the square root of this. Lambda 2 becomes lambda. 4 becomes 2, a square root of pi, and 10,000 here becomes 100. So this is what I'm going to have, and I'm probably going to have the approximate value for my A here, and that A is approximately, so that's going to be approximately 29 lambda. So this is 29 lambda approximately here. So this is 29 lambda for me, and let's now check what this 29 lambda means. This 29 lambda means when you have a horn antenna with this aperture, which is A and B, so this is your horn antenna, and this A is about 29 lambda, this is about 29 lambda. Now let's set a frequency. For example, let's say frequency is 10 gigahertz. Then lambda is C divided by F, 3, 10, 8, 10, 10, 9, and that's going to make it 3 centimeter. So your wavelength is 3 centimeter. Now 29 times lambda, if you approximate 29 by 30 lambda, so 30 lambda times 3 centimeter, and lambda is 3 centimeter, that's going to make it 90 centimeter. So 90 centimeter, although it is big, but it's not too big because you are having such a high directivity. So at this point you might say, okay, if I make a horn antenna with the aperture close to 90 centimeter, probably I can get close to this. And that's actually correct. If you do that, then you can get to 10,000 directivity. Keep in mind that we did some approximation here. For example, we assume aperture efficiency is 100%. Now, but there is something that we have missed here, and I'm gonna go over that. So you see, this is the size of aperture. You essentially need about 29 lambda by 29 lambda to get to the aperture that you need to get to 10,000 directivity based on aperture efficiency of 100%. Now, let's go and see where the problem starts. The problem is not with the aperture size. The problem is how you're gonna make it to the aperture. So if you remember, when we wanna get to the aperture, we need to start from a waveguide. So we start from a waveguide. For example, here is 10 gigahertz. So if I wanna make this aperture, I need to start with the waveguide WR90, which is the waveguide for X-band. Now I'm gonna, and this is for my E-plane, and I'm gonna start expanding into my aperture to get to my, in this case, capital B. So, and then you remember that we had an equation, and this equation tells us that this length minus this length should be a certain value, because, so in this particular case we had L minus R should be approximately 0.25 lambda. This is the equation that we have. This is for E-plane, so we had subscript E in our previous discussion. We had a different thing for H-plane, but I'm using that. The other one results in the same conclusion. So by looking at that, this essentially means L and R cannot be so much different, because if it's so much different, you see everything when you travel along the waveguide, this electric field in the fundamental mode that's passing is in phase. But when you get to this point and then you go to different path, you start developing out of phaseness, because you are traveling different distance. This one would be this distance. To get to the edge, you're traveling along this path, and therefore you develop out of phaseness when you get to the aperture. And out of phaseness is bad, so you need to control it to not exceed certain level. And this is the equation that we follow. We say these two should be relatively close. Now, this is the problem that we're gonna have. Now, we calculated based on some approximation that, for example, A and B are equal, and we got to the point that B is 29 lambda. So this distance that we have from here to here, that's gonna be half of B. Half of B would be 14.5 lambda. For simplicity, let me just assume 14 lambda makes my calculation easier. So this half should be about 14 lambda. So it should be 14.5 because everything is approximate. Let's just go with 14 lambda. So I need to get to 14 lambda here. Therefore, that gives me an equation. And the equation that it gives me is that L2 plus R2 R2 plus 14 lambda to the power of 2 should be L2. So you see, in this triangle, R2 plus 14 lambda to the power of 2 should be equal to L squared. And I also know that L minus R is 0.25 lambda. So this is also what I know, and I can actually use this and write L2 minus R2 equal 14 lambda to the power of 2, and I can use that as L minus R, L plus R, 14 lambda to the power of 2. I already know that L minus R is equal to that, so this is 0.25 lambda, therefore I can find L plus R. L plus R becomes approximately 784 lambda based on this calculation. So you know this, then you can find this. So now you have two equations and two unknowns. Now you can find, for example, length L. So if I find length L, I can just add these two equations. 2L becomes 784.25 lambda. So this becomes my L, and I can calculate my L as 392, approximately 392 lambda. Maybe if I just use the decimal point, it's not a bad idea, 0.1 lambda. And R, once I have L, I can find my R, approximately 391 point, if I go with one decimal point, 0.9 lambda. So if you look at this calculation that I have, you immediately notice something, that L and R are extremely close. So they're extremely close, and if you use more decimal point, you see that their difference is 0.25 lambda. So they're extremely close. That's a big message for us, that to get to this big aperture, 14 lambda, we need to go very smoothly. We cannot just go abruptly to the big aperture. And now this essentially tells you the size of the aperture is not big. The distance that you need to travel to get to the size of the aperture, that's gonna be big. Because now look at the issue that we have. We have 391 lambda. So, and lambda is 3 centimeters. So what's gonna be the length? So you have 391 lambda almost. That's gonna be the point that you must travel. You need to multiply it by 3, and then you get your you get to about 1173 centimeter. So that's a huge distance. So let me double check that. 3 and then 27, you get to 1173 centimeters. So that's a huge distance. You're looking at about 11 meters to go from WR90 to the aperture of the horn, and that's so much. So your antenna in terms of aperture is not too big. It's the distance that you travel is so big. So if I want to plot it here, so essentially that means if you have a waveguide which is WR90 and you want to get to a big aperture, you need to go very smoothly, like that, to get, for example, to this aperture size. So you see the aperture is not too big. The distance that you travel is too big, because at the end of the day, this red path and this black path here, they need to be very close by this distance. So that essentially brings us to the problem of designing such big directivity with horn antenna. So people have done that for different reasons, but for a standard typical applications, if you want to use horn for such directivity, then you pay the price on the length of your horn. So that's why we need a different antenna to get us to these huge directivities, like for example 40 dB, and that brings us to the topic of reflector antennas. Okay, we just learned that if we want to make a very directive antenna using horn antenna, we're going to have a problem, and that problem would be the fact that the transition to the big aperture needs to be very smooth, and therefore the length of the horn antenna becomes very large. So that's what we learned in the first part of this lecture. Now, to handle that, we're going to study a new antenna, which is reflector antenna. So this would be the topic of our lecture, reflector antenna, or as known as dish antenna. So this antenna is actually creating a large aperture for us with reasonable phase and amplitude, and it doesn't need to have a very long length. Remember that at the size of the aperture needs to be in a way that can make the directivity that you want, but then here we're talking about the length, the compactness of the structure. So, but the size of the aperture is coming from the fact that if you want to have a D naught, so you're gonna still have an aperture efficiency and a physical aperture. So for example, to get to 40 dB directivity, 10 to the power of 4, you need a certain physical aperture for horn antenna or reflector antenna. So that stays, that needs to be still big, but how long you need to travel to get to this aperture, that's essentially the question. So now to start a reflector antenna, let us first start with the structure. So imagine you have a parabola. This is a parabola, and this is the axis of the parabola, and you rotate the parabola around its axis. So if you do that, you get a three-dimensional structure called paraboloid. So this would be the type of reflector antenna that we study in this lecture. It could have different shape, but this is the shape that's the focus of our discussion. So this is a paraboloid. So you get parabola, then you rotate it about its axis, and you get a three-dimensional structure, paraboloid, or we call it dish, for example, in this structure. And of course, the material here is metal. So it's a metallic structure. So you expect that if you have an electromagnetic waves illuminating this metallic structure, it needs to reflect because that's a metal. And we're gonna consider the ideal case, perfect electric conductor for this. So that's our paraboloid. Now, to understand why paraboloid gives us this benefit of creating a very reasonable aperture, we first need to look at its mathematical equation, so the geometry of this. So this is not going to be EM, this is the geometry right now. So let's start studying the geometry of this paraboloid. So for that, we're going to consider this. So let me get rid of this to have a better picture. So imagine you have your paraboloid like that. So, and if I consider a two-dimensional cross-section of this, this is essentially, let's consider this to be Z, let's consider this to be X. So parabola has a focal point. So let's assume the focal point is at the origin. So the length from here to the origin, it's called focal length. So this is my focal length. So that's one parameter that I have. So this is my focal point. So that's my focal point. And this point here is called the apex of the reflector. So that's the situation that I have. Now, mathematically speaking, if I want to represent that, I can represent this with this equation that x squared plus y squared is equal 4f f minus z. So that's going to be the Cartesian equation that describe a paraboloid. So remember, this is a cross section, but because I'm representing the three-dimensional form, I'm going to have x, y, and z, both of them. So this is just the xz plane that you see. So for the three-dimensional case, you have something, you have this curve. And I think the magic is in this equation, as you'll see. So you need to pay attention to this equation. So, but first, just take a look at this, and we see that if we want to identify our paraboloid, the only parameter that you need is focal length, because x, y, and z, of course, are the coordinate in the three-dimensional space. So if you know your focal lengths, you can create a reflector. So as soon as you decide on your focal length, you can just plug it here and plot your curve. So that's something to notice here. But if you do that, you're gonna get a paraboloid that essentially goes to infinity like that. It just continues. So, but for fabrication purposes, we need to somehow truncate this curve. For example, as you see here, we truncated at this point and this point. So when we truncate it, we end up with a diameter that we call d. So essentially, for physical fabrication, not only you need to know your f, but also you need to know your diameter, which is capital D. So if you want to fabricate this, you need two parameters, f and diameter d. So that would be the diameter of reflector. That's an important quantity because that shows how big is your aperture size. So for example, if we consider capital D as the diameter, then you can calculate the area. As you'll see, that's going to be PD squared divided by 4. Perhaps maybe we should first take a look at the area based on capital D. So the question is, what would be the area of this curve? Or maybe, I mean, sometimes some people, instead of considering this aperture, they might shift the aperture to here. That's essentially the same curve. It's just shifted here right on the focal point. So in terms of area, they're the same thing. So if I ask you what is the area here, to calculate the area, of course, you need to know the shape of this curve, this closed curve. So based on, if you want to understand it, probably you need to look at the equation. So how do you find, for example, what is this shape? So you would say, okay, this is located at z equals 0. See, this is my z axis. This is located at z equals 0. So understand this cross section, I need to plug z equals 0. And if you plug z equals 0 for this particular cross section, you get 4f f minus 0, and then you get x squared plus y squared equal 2f squared. So you're going to have something like that. And if you look at this equation, you see that's a circle. So essentially the cross section here, so that means the aperture of the paraboloid is a circle. And this circle has a diameter. The diameter is d. So the physical area, which we denote by AP, is going to be pi radius d divided by 2 to the power of 2, which is going to be pi d squared divided by 4. So that's essentially the cross section of this reflector. And this is, as you know, is going to be related to directivity later on. So far, let's see what we learned so far. We learned that this is the equation of the paraboloid, and to determine our paraboloid, we need f because of the equation. Then we need the diameter d because we want to know how to fabricate, what would be the extent of this paraboloid. So we need these two parameters. Usually in antenna engineering, we say we need f and f divided by d, which is the same thing. So if you look at this, either if I give you these two or these two, this is the same thing. But the nice thing about f divided by d, which is called focal length to diameter ratio, is that it gives you insight about the curvature of the paraboloid. So, for example, let me let me have a couple of things here. So imagine this is my z-axis, this is my x-axis, and this is the focal point, which is the origin. So now if FD is equal to 1 divided by 4, you see that this is going to be my paraboloid. Now, if FD becomes, for example, 1 divided by 3 for the same diameter, so I'm just keeping this same diameter, this is going to be my paraboloid. And now if f divided by d become half, this is going to be my paraboloid. This is based on, you can see a picture, accurate picture of that in the book by Professor Stutzman and Thiel. But this is just, I just plotted like that here, but for more accurate version, please look at that book. But the message here is that if FD, as you see, increases, the curvature reduces. So you see you have more curvature here. As you increase f divided by d, the curvature reduces and so on. And if f divided by d goes to infinity, essentially you're going to have a flat surface. So like this, you're going to have a flat surface because curvature reduces. And okay, so in summary, we mentioned that now we can represent our reflector antenna by a factor f, focal length and focal length to diameter ratio. And the advantage of this representation is that you can somehow understand the curvature of your reflector by noting that the larger f divided by d, less curvature you're gonna have. So let's then elaborate a little bit more on the geometrical side of this. So that's one thing that we have here. X squared plus y squared equal 4f minus z. And at this point, it's to understand why this reflector is such a useful thing for us. It's actually good to convert this to a spherical coordinate. So let me keep the equation here, but then let me just represent my reflector by in a 2D cross section, and then I try to convert that to a spherical coordinate. So to convert it to a spherical coordinate, we know that instead of x, y, z, I need to represent based on r, theta, and phi. And you know that theta is essentially the angle calculated from z-axis. So this is my theta, and of course this is my r. So you have your r, you have your theta, and then this is x, and y is going into the whiteboard, and phi is essentially the angle calculated from x and goes in the xy plane. So you don't see it here because it's a 2D cross section. I need to have it in 3D, and then you see as you rotate like that along the xy plane, that's the variation of phi. Now to convert that to r, we already know that r2 in a spherical coordinate, that's going to be x squared plus y squared plus z squared. And I already have these two here, so I'm just going to add z squared to this equation. So let's do that. So let's add z squared to this equation. So I'm going to have x squared plus y squared, and this is going to be the addition of z squared that I have, and I have 4f minus z. I'm just going to write it as 4f squared minus 4fz, which is that. Because I added a z squared here, I'm going to have to add another z squared here as well. So now if you look at this system, you know that this is essentially your r squared. And now this is, you can simplify it by saying 2f minus z squared. So you have that. You take the square root, r becomes 2f minus z. So that's going to become my r. And you might say, why don't you have, because this is in fact plus minus, but then why did I not choose minus? Because then that's not a physical solution. Based on a spherical coordinate, r needs to be positive, and this solution ensures that my r is positive. And you can realize it here because this from here to here is, this distance is f. So the remaining z are all smaller than z. So 2f minus z is going to be positive for me. So this is the situation that we're going to have, but this is still not a spherical coordinate because I have this z over here. So I'm going to convert that z to a spherical coordinate as well. And this is very easy because you know that r, so if you, for example, look at z here, which is this distance from here to here, because that's z axis, z is r cos theta here. So based on that, I can substitute for r cos theta, and I'm going to have r equal 2f minus r cos theta. Then r1 plus cos theta becomes 2f. Therefore, r becomes 2f divided by 1 plus cos theta. And that becomes the same equation. This is the Cartesian representation. This is going to be the spherical representation. And this spherical representation is better to see what's happening with the reflector antenna, that we can have a big aperture with reasonable phase or with uniform phase uh, in relatively a smaller distance compared to what we saw with horn antenna with high directivity. So this is really important. Now, so this is the Cartesian one. This is the spherical one. As you see in Cartesian, the curve is determined by f. Here, r and theta is part of a spherical coordinate. And because it's the way that I have my reflector antenna, this reflector antenna is you have a parabola, you just rotate it around the z-axis. So essentially you get an axisymmetric reflector antenna. So when it's symmetric in the rotation, is not going to be dependent on phi. So therefore you didn't see phi here. So that would be, compared to this, an advantage for this representation. You don't have the phi, so you just need f to represent it. And also you still need the diameter to see how big is your reflector, or where mathematically to truncate your curve. So that's our spherical coordinate. Now let's focus on this and see the advantage of a reflector antenna. So let me remove this, and now I'm going to go to that equation. So again, assume that this is my z-axis, this is my x-axis, and this is my reflector. This is my focal point, which coincides with the origin. And now I'm going to pay attention to this equation. Let me write it here. So the equation is r equal 2f 1 plus cos theta f. Let's identify f again. This is apex. So this distance is f. So that's 2f1 plus cos theta. Let's also show, for example, 1 theta here. So if I have this line here, this angle, of course, is theta. It can be any point, so the theta will change. So this is, for example, let's call this O, let's call this A. So now, so what's happening here is that if you look at this equation, let's see what we see. If I multiply this by the denominator, I get r1 plus cos theta is 2f, or I can just open it and write it like that. So this is perhaps one of the most important thing here. You need to understand this. And I want you to pay attention here that this side of the equation is constant. So as soon as you design a reflector with a constant f, this side of your equation is constant, 2f. That's here. Now let's recognize what is r. So r is the distance from origin to any point. So for example here, this is my r. So I can just maybe write OA. This path length is r. Now what is r cos theta? So if you have this distance here, let's call this B, and AB is parallel to the Z-axis, then if you look at here, this is in fact r cos theta, because if you project r on this axis z, you get r cos theta here. So let me do that here, maybe with the, so if I project r, this is in fact r cos theta, which is the same as AB. So now I can just write that this is AB, and that's going to be 2f if I add these two path lengths. That's actually quite amazing, because this point A can be any point on the reflector. Let me choose another point. For example, let me first get rid of this. Okay, now let's choose another point. Let's say, for example, this point. Let's call it A prime. Now, what is this distance in a spherical coordinate? Of course, this is r, but this is a different r. This r and this r are different, but in a spherical coordinate, they are r. I mean, this r can change from the point here to another point here. For example, when you write the Cartesian curve equation, you know that x and y and z can vary. The same thing with r in a spherical coordinate. But now, this is my new r for this point. So now, this time, this could be, for example, the path OA prime. So from O to A prime. Now, what is if this is r, now I have a new theta as well. This is my new theta. Remember, this is not the same as that. This is my new theta. And now r cos theta is going to be, now this is B prime. Now this is your new r cos theta, because if you project it here, now this from here to here is r cos theta, which is equal to A prime B prime. So this is my A prime B prime here. And amazingly, this is also going to become 2f. So you see, if you go to any point on the paraboloid, and then you go back parallel to the z-axis, and then you add these points, they're going to be the same thing. You can do it for another one, for example. Let me do it, for example, for this one here. So let's call this A double prime, and then you go back like this, and we call it B double prime, and that's going to be OA double prime path plus A double prime B double prime equal 2f. So all these paths are becoming the same. Now you start understanding something. You can get a feeling here that this is very useful in antenna engineering, because what was the problem with the horn antenna when we wanted to achieve high directivity? Remember, the problem with horn antenna was that when I had something like this, so whatever I do, I'm going to have, of course, different paths, right? So, and that was the problem that I had when I wanted to design high directivity horn antenna. So I needed to go very smooth. So the dimension of the horn antenna from this length becomes very large, because I needed to go very smooth, so that this distance and this distance and this distance are similar relatively. Now imagine this situation, that reflector gives us something that the distances are all becoming the same. So that's actually quite amazing. Now for a second, let's make this assumption, and this is a correct assumption, but I'm going to come back to that later. Let's assume that we put a point source here, so on the focal point. So this is something that we're going to call feed of the antenna later on. So we're going to put a source at the focal point, and when we put a source at the focal point, this source is going to illuminate the reflector by some rays. So let me have a cleaner picture here. So again, this is my x-axis. This is my z-axis. And I'm going to put a source here. So for now, assume that I'm going to put a point source here. I mean, practically, this is usually a horn antenna that you place at the focal point. And assume that you have some rays traveling toward the reflector like that or like that. So you have some rays, and you see, I use rays. I mean, we have wave propagation, but I'm saying rays, and this is part of something that we call geometrical optics. So this is because the structure of reflector is usually extremely big compared to wavelengths. Geometrical optics, which assumes we are dealing with rays, would be a reasonable model that we are using here. So this terminology that I'm using, rays, is based on this geometrical optics. We could go to other model like physical optics and things like that, but this is our focus here. So again, you have some rays going toward the reflector, and as based on this model, the size of the reflector, remember, is big. We want it to be big because we want high directivity. So now, if the reflection from the reflector is in a way that the reflection is parallel to the z-axis, which is in fact the case, but I'm going to come back to this. So if the reflections, because this is a metal, so this is a PEC, so it's going to reflect 100%. If it reflects in a way that the reflection is parallel to the z-axis, you get something quite amazing, that if you start, for example, with the phase of 0 here, if you assume this is the phase of 0, when you arrive here, the phase would be e to the power of minus jk times distance that you travel. What is the distance from here and here? We just show that all of them are 2f. So 2f is distance. And amazingly, for this one is also minus jk 2f. So you see, all these phases become the same, assuming that you have a point source located here. Now you get a very nice aperture here. So this is the aperture that I have, which you know it's circle, so it's a two-dimensional. So now you see a line, but in practice you see a circle here, and everything on this aperture is going to be completely in phase. And this is because of this amazing property that we have. I could do it for one more here. For example, it goes here. Again, reflection is parallel, and as long as it's parallel to the z-axis, this is completely satisfied. The phase at this location would be minus jk times distance, which is 2f. So look at that, how beautiful it is, and compare it with the horn that you were not able to satisfy that. Now, remember, for the horn, you needed to have a very long horn to get to reasonable phase here, but the only length that you needed here was actually f. From here to the apex is f. So that's the importance of this equation. So my suggestion for you is that when you are looking at the equation of the reflector, look at this equation like this, which conveys this message that the addition of these two adds up to be a constant number twice the focal length.